much, first of all, for giving me the opportunity to present today my current work with Vero and with one lines. Today we'll talk about generalized disformal transformation in the framework of geometric mechanics, linking to what Vero already told you in the mini course yesterday. We'll start by introducing the physical motivation behind our problem, and then move to the geometry. So, modified gravity is a term that refers to the several extensions of general relativity that have been put forward by theoretical physicists in the last 30 years to explain the mismatch between the predictions of Einstein theory and the observation coming from cosmology. And the interest in disformal transformations and their generalizations comes from the fact that they have been shown to relate several of these models. Now, the name disformal transformations is protected in physics. It refers to the Bekenstein's original disformal, which involves in particular the coupling with the gradient of a scalar field. So if we look at this kind of transformation in the space of fields, those transformations are higher order, and this will be relevant for our proposal of definition of generalized disformal transformation in the geometric mechanics framework. Now, the purpose of studying those objects is then double. First of all, we want to eliminate redundancies between already existing proposal. It would be nice if we could characterize, classify in equivalent classes our modified gravities to concentrate on the simplest representative of an equivalent class. And on the other end, as Vero was already telling you, we are interested in building new theories out of existing ones in such a way that we control the physically relevant properties, the degrees of freedom that were the subject of the topic of today, and global stability, which will be the topic of tomorrow's Vero mini course. We started to study the problem in geometric mechanics, and in particular, I will just lightly review the notions of higher order tangent bundles, because these are the bundles that appear in the description of our models. And as Sophia already introduced you this morning, the k-factor tangent bundle is just the space of equivalent classes of curve up to order k. So the k-jets of our smooth curves at 0. And if one chooses coordinates on a manifold, we get orthonomic coordinates on the tangent bundle, which are just the accelerations up to order k of the coordinates, and we have natural projections of the higher order tangent bundles into the lower order ones, which are just given by deleting the extra accelerations if one looks in coordinate. Now, given a map of smooth manifolds, we can lift it to a map of higher order tangent bundles, and the expression in coordinates of this map is just given by the derivative of the function, total time derivative with respect to time of the function with respect to the coordinates we have chosen. Now, our proposal of definition of generalized disformal transformation in geometric mechanics is a subjective submersion from the tangent bundle of a manifold to the manifold. Now, this map plays in our study exactly the role that a diffeomorphism of the manifold would play. So this is quite not a non-standard object, because in particular it's not a diffeomorphism, it involves a change of order from target to domain. And this map in particular is not a basepoint preserving map. It's an arbitrary map from DQ to Q. We want to define the analog of the orthonomic lift that I introduced in the previous slide, namely the map that in coordinate are just given by the total time derivative of our GNDs. In this you can see the intrinsic definition in terms of the tangent lift defined in the previous slide, tk phi, and the canonical inclusion of tk plus 1, the k plus 1 tangent into the k tangent of the tangent. This is a bit technical, but in coordinates you can see what this map have to do. And if we put manifolds of the same dimension at the same level, we see that the defining feature of disformal transformation in the orthonomic lift is that they relate bundles of order 1 of difference from one another. So let's come back to the purpose of studying those objects, namely building theories out of existing ones. So what we do is we start with a first order Lagrangian on DQ here, and we put it back along the first lift of the map to obtain a second order Lagrangian on T2Q. This is what physicists mean by applying the transformation on the level of the disformal, just pulling back along the first lift. This is exactly the same as what we would do if we had a diffeomorphism of Q we would obtain a new Lagrangian by pulling back along the tangent of the map. And now, we have two Lagrangian, L prime and L. We want to relate them. In particular, a second order Lagrangian has phase space the third order tangent bundle, and so the relevant map to relate the two theories is this decomposition of red arrows in the diagram, the map I will call phi. And we want to relate the presymplectic triples associated to the two Lagrangians. Let's start with an example. Harmonic oscillator plus free particle. The configuration spaces are 2. We can compute equations of motion, energy, and two-form associated to this Lagrangian. We now consider the following GENDs. And we obtain a Lagrangian L prime, which is a second order regular Lagrangian. The first question we want to ask, we may ask ourselves, is whether the equations of motion associated to this Lagrangian are simply given by the pullback of the original equation of motion. And this is not the case. We can see on the left the pullback of the seed equation of motion, on the right the equation of motion associated, the equations of motion associated to the new Lagrangian, and in particular, every solution of the seed system pulls back to a solution of the transform system, but the new Lagrangian has more dynamics. The systems admit more solutions, and so it's potentially able to describe more physics than the original one. We have more dynamics. This is important for the cosmological purposes. Now, we try to relate also the geometry of the system, and in particular, what we find out is that the transform energy and two-form are not just simply given by the pullback along phi. Phi was the composition of red arrows in the previous diagram, but we have extra terms that seem to be related to the pullback of the seed equation of motion. So this simple example is teaching us two important things. We have two theories, but the solutions and the geometry of the systems are not directly related. The new systems have more solutions than the original one, and we have extra terms that prevent us from directly relating the geometry of the two systems, energy and power. Now, we want to understand what this failure is, and we define the disformal defect in this way. This is the same basic form K, which is this object here. J star is the dual of the canonical almost tangent structure of order 3, which is a 1-1 tensor on T3Q, which has the following coordinate expression, while delta L is the Euler-Lagrange form on T2Q. So it's the form whose coordinate expression, whose components are given by the Euler-Lagrange equation associated to the seed Lagrange, and we pull it back along the second lift of our GENDs. Now, in full generality, Lagrangian energy and two-form of the transform system can be expressed as the pullback of the original one along our map, comparing map phi, plus extra terms, of which you can see the coordinate expression on the left and the intrinsic expression on the right. Those depend on the disformal defect. In this case, those add the mass that takes a semi-basic form that assigns to it the corresponding function, and in this case we have the differential. Similarly, we can try to relate the dynamics of the two systems. So we express the Hamilton equation of the transform Lagrangian as the pullback of the Hamilton equation of the first Lagrangian plus an extra term, which is the Lie derivative of the disformal factor. The only caveat is that the push forward of a vector field is not a vector field in general. And as the example already taught us, the equations of motion associated to the new Lagrangian are not simply given by the pullback of the original one, but we have this more complicated expression. Now, in the introduction, I told you that one of the purposes of our study is understanding whether we can classify equivalent theories to concentrate on the simpler representative of an equivalent class. And we start again with an example, same seed as before, but we consider this disformal. And we obtain a Lagrangian L prime, which is again second order, but it's a singular Lagrangian. And it's a very simple Lagrangian. We can perform the constraint algorithm, and what we find out is that in this case, the pullback of the seed equation of motion appears as a constraint of the transform system. So in particular, the new system has no more dynamics, no extra dynamic appears in this case. And similarly, we can try to relate form and energy. We have extra terms, but as you can see, the extra terms contain the pullback of the equation of motion. So they vanish shell. If I go to the final stressor manifold, Lagrangian energy and two-form are just the one coming from the seed system. So we can relate exactly the geometry and the dynamics of the two systems. In particular, this is the expression of the final stressor manifold, which is clearly diffeomorphic to the TR2 on the left side of this diagram via the composition of red arrows, and moreover we can write an explicit symplectomorphism from the final costal manifold of the transform system and the original phase space of the original Lagrangian. So in particular, what is different from the usual setting? Usually we have a diffeomorphism at the level of the configuration space, which lifts to a symplectomorphism at the level of tangents, or cotangents if we are working in the method. In this case, we don't have a map on the base, but we recover a symplectomorphism at the level of final costal manifold. Now, we would like to understand how general these features are, and we have found a sufficient condition for this to hold, namely this definition of the nilpotency, which is the system of coordinates in which this matrix C is irregular, and this object B is strictly lower triangular. Now we are still trying to understand the nature of the geometric nature of this object, which is related to the kernel of the tangent of the first lift of the Disformal. Its coefficient transform as the inverse of a connection coefficient, but we are trying to relate to the nilpotency of some object constructed out of some algebra constructed out of this kernel, but we are still working on it. But the important thing is that whatever Lagrangian we choose, for an nilpotent GNDs, the pullback of the Lagrangian we obtain by pulling back along this map is a singular Lagrangian. And we can prove the following theorem, namely that the inclusion of the final costal manifold into our phase space pulls back identically the Euler-Lagrange form of the system. So in particular, the pullback of the original equations of motion are constraints of the transform system. So in this case, we always recover the dynamics of the original system. No extra solutions appear. And by looking at the expression of the extra terms that were appearing in preventing us from relating directly energy and two form, those objects, the extra term vanish if we go to the final costal manifold. So those map also allow us to relate the symplectic structure of the transform system. Now, if in particular the composition of blue arrows in this diagram is a diffeomorphism, what we get is a symplectomorphism at the level of final costal manifold, recovering what we were trying to mimicking what happened in our very simple example. And we are trying to understand what are the extra conditions, if any, we have to impose on the GNDs for this to happen. Coming to the conclusion, we have proposed a definition of generalized Disformal transformation in the framework of geometric mechanics, which allow us to build Lagrangians of different order with respect to the seed ones, in particular of order 1 of difference, but we could generalize to higher order. And these Lagrangians describe in general new dynamics. So the underlying physical system we would like to describe in the field theory setting will have a different and more rich phenomenology than the starting Lagrangian. And for the purpose, instead of classifying equivalent theories, the nilpotence condition is pointing toward at least dynamical and geometrical equivalence. I mean, as Vero already told you, we don't have a precise notion of what physical equivalence would mean, but this certainly points in this direction. For the outlooks, we would like to better understand the nature of this nilpotency condition, and because we want to understand if it's necessary for the Disformal defect to vanish on shell. Remember, the Disformal defect was measuring our failure to relate the dynamics and the geometry of the two systems. So if we better understand this object, we can both characterize better the extra dynamics that appear and understand this nilpotency better. And we would like to understand the relation with the symmetries of the seed transformal Lagrangian connected by this kind of map. And later we would like to move to the field theory setting, since this is the real setting where these questions are motivating from the physical point of view. So we would like to come there eventually. And thank you very much for your attention. I'm open to your questions.
Questions? Could you come back to slide 17?
Yes.
That's the question.
Thanks. Was the answer correct?
Yes.
Is this, under your definition,
I guess this is not a tensor that you say this.
Yes, this object B is not a tensor.
But I expect this condition of being lower triangular doesn't depend on the coordinates, right?
It does, because the object, I mean, when you do a coordinate transformation, a lower triangular matrix can become.
Yeah, but your condition of nilpotency depends on the coordinates.
I mean, the definition does not depend on the coordinates. I mean, the definition, if there exist coordinates, we have these. Of course, the fact that this matrix is lower triangular and this is regular depends on the coordinates, yes. And we are trying to find some geometric object that captures these, and we are trying to relate it to this kernel here. In particular, Manuel was thinking to relate it to the to a Lie algebroid we can construct through the kernel of the file. Yeah, me too.
Yeah, so you said at the end about wanting to kind of, I think I understood, sorry if I misunderstood, like look more into like the dynamics and like the differences that you see between the dynamics of your seed Lagrangian and the new one that you generate. Is there any indication at the moment that, like, do you have any sense of like how they might like be related? Can you tell anything about the new dynamics from the seed ones, or is it?
We didn't look at it already, but what we think, if you look at the equations of motion, in the general case, those are the pullback of the seed equation of motion. The extra time is somehow related to this object here, and so the extra dynamics is somehow coupled to the original dynamics. We cannot factorize the dynamics in two parts, one independent and one on the other. But the original dynamics is really linked to the extra dynamics that appear. In this sense.
I have another question.
Yeah, go ahead.
Yeah, again, you might have said it and I missed it, so apologies if so, but you talked about relating the symplectic structures and finding that
Yes.
they were equivalent. So that's really interesting. Did you do anything with like the conserved quantities of like the systems that the Hamilton?
No, not yet. It's exactly what we want to do when we look at symmetries. It's our next objective.
Oh, okay, cool, great.
Any questions? Good. Then let's thank Matteo once again.